Fine, very good. So yesterday we were talking about, I mean, in last class, we were discussing about these elastic strains, and we were trying to discuss those elastic strains in continuum model, within continuum model. So I'm sure you all are now familiar with what is the continuum model, how we can generalize Hooke's law for a three-dimensional body. Okay, before we move further, let me ask you if there are any questions from your end, or you have some confusions which we can try to discuss before we proceed further. Yes, please. If there is any question, please feel free to ask, and let me know if I can help you. Okay, so if there are no more questions, let us now proceed further. We were discussing that we can design the vectors, some three mutually perpendicular vectors. Rather, those we may decide to be unit vectors, that is the vectors of unit length, and then measure the deformation in terms of how these vectors deviate from their original position, which is the unit length, and they are mutual perpendicular to each other. So how do these vectors deviate with respect to their original position, which is for a unstrained body? So now, in case, so I hope you remember now that these epsilon xx, epsilon xy, these all are representing deformations of the 3D body, which we have already discussed in detail in our previous class. So if we follow up with this value of x dash, that is new vector, then what should be x dash dot x dash? I think this also was done in the previous class. So this is given by this expression, just taking the dot product. And this, if we ignore higher order terms, we can only retain this up to first order. So that's what is the change in length of x vector there, or the vector along x direction, so that any point within the body of the cube, which is located at any point, say R, within the three-dimensional body. I mean, let us say this small cube as unit cell. Let's not confuse it with the unit cell of the crystal structure. What we mean here is that, okay, this is one smaller portion of the bulk body, which we are studying under particular conditions or under the effect of strain. So that cube is representing a smaller portion. So, I mean, the strain, although is in whole body, but we are wanting to measure it in terms of one small portion, so that then we can generalize it for the whole body. That's what is the idea here. So any point, say, which is located at any position, say R, in that in those reference vectors, let us say this one. So suppose we have a point, say R, located somewhere with coordinates x, y, z. Then here, what will be the location of that point in terms of original or unstrained lattice unstrained vectors, not lattice vectors? This will be like this, and the location of the same point after strain is applied or stress is applied on the body can be written with the help of this. I hope this is clear up to this. Then the net displacement which this point has suffered due to strain can be written in terms of this vector, which we can call R, capital R here actually. So this is just standard vector analysis, how we can find out the displacement. And this can be obtained like, okay, x is common in both. So the coordinate remains same as I had discussed in the previous class as well. X dash vector minus x vector, these are the unit vectors along the two different directions. Now we have discussed that in detail. So that is how we can write down the displacement. Now, if we, I hope I had given this as a homework to you. I remember it well. So I hope all of you have done this homework. Have you done it or no? Have you done it? Have everyone done it or have someone done it at least? Harish says he has done it. What about others? Anyone else who have done this? We had just to expand these terms and then obtain this expression which is appearing on your screen for R. Anyone else who have done it? Let's be honest. No one? Very strange. Please make sure that you do your homeworks which are given to you, because here on the PowerPoint screen we can't do each and every step. So the best part is that, okay, I give you certain guidance and then you follow those things and do these yourself, because at the end of the day it is your practice which will be helping you. Otherwise it doesn't make sense. I mean, I keep on talking and you keep on listening and we don't do anything practically, so that won't make this communication effective. So please pay attention and do whatever has been given to you. If you face any problem while doing this, then I will be there to help. Okay, let me ask it other way. I mean, did any one of you face problem and you couldn't reach to the final step? Yes, anyone faced a problem? Yes, no, at least some response should be there. Okay, every one of you write down, okay, let's hold. All of you write down what was your reason. Either you have done it, then you write down yes. If you have not done, then write down no. If you tried but couldn't get it, then write down tried. So let me record the responses. How many of you did what? I will appreciate your honesty. No issue even if you have not tried, but answer honestly. Yes, please. Good. Fine. Everyone should respond. I mean, I'm recording your responses, so I want to know what was the situation. Tried. Okay. Okay. Fine. I hope everybody have recorded their response, because this is also part of your attendance. No problem if you didn't try, but I would request you to do things. It would not have taken, I think, more than 10 minutes of yours. And these small practices makes you confident on what you are going to do. So this will, I mean, this can be obtained very straightforward. You just have to put x dash and then minus x. This is very simple. Rather, if you take this equation itself, multiply this will be x dash vector, that is equal to 1 multiplied by x cap. So this will be x cap plus epsilon x into x cap plus everything else. So we take this x cap to the left hand side. This is nothing but x dash minus x cap, right? So this is this thing, I think. Yes. Okay, they have taken certain things common. Okay, I mean, then they have arranged all the terms. I mean, there will be one term coming from here which will contain x cap, which will be nothing but exx into x cap, correct? Similarly, there will be another term coming from this y dash minus y cap, that will also be containing, eyx. So here is this, and because this first term is multiplied with x, so this is why it is x into exx or epsilon xxx, whatever you want to say, y into epsilon yx, similarly z into this. That is how you can get these terms. This is very simple and straightforward. Well, then let us write down this function r in terms of some variables, like say u V and W. So I think Rahul or Sandeep, any one of you was asking a question that how that kind of strain can be measured in experiments. So I don't know if you have done experimental fitting or fitting on experimental data by using Ritwell refinement. So there we also come across those UVW parameters. So those UVW parameters can be related to this one. I mean, they are trying to find out if there is any strain in the crystal. Okay, so bulk strain in the crystal, UVW parameter. So what U contains? U contains the net displacement or net X component of the displacement, which is coming from all these. Then V contains Y component of the displacement, W contains Z component of the displacement. This one, okay? Now, from here, if we use this form, now UVW are not at all defined. We sort of ad hoc way brought in these UVW. So how to define or how these UVW are related to these? So basically from here, we are not exactly finding UVW as such, but yes, we are trying to find out what is the relation between these deformations and UVW. So if I take this one and then compare the terms, what we can find out, rather we are actually using, okay, let us use Taylor series expansion of this. I hope you are familiar with Taylor series. You have a function, then expanded around a certain point. Then you have first order partial derivatives, second order partial derivatives. We are ignoring second order. To certain extent, we will have to keep second order derivatives. So what will be x into exx if we see from here? So if I take first order derivative of this with respect to x, so what will this give us? Del u over del x will be what? From here. So you have x, y, and z dependence, correct? So if I take x dependence only, then what is that? That is related to exx. I hope you are able to get what I'm saying. So del u over del x will be nothing but related to exx, or a term x into del u over del x is related to x into exx. Why this x is sitting here? This comes from Taylor series. So suppose we are expanding this function around, say r is equal to 0. So r is equal to 0 means small x 0, small y 0, z 0. Because x, y, z are coordinates of the point. So if that point is at 0 or origin or reference point, then we will say, okay, x, y, 0, z 0 being the reference point or origin. Then Taylor series will be like, okay, if you are at x point, then what will be that? Usually we write x minus x naught into first order derivative. I hope my oral communication is sufficient to convey it, because I have not put all those details here. Had I been working on on a board, then I would have written it quickly. But I'm sure it's not that difficult. You all have done Taylor series. So what is that is, okay, function at say point x naught plus delta x is equal to function at x naught plus delta x, which is nothing but x minus x naught, correct? Into del f over del x. If you have a y variation as well, then we say, okay, delta y, which is a y minus y naught into del f over del y, right? If we have a three-dimensional function, then we have del z plus del z, del f over del z. So that is from where we have got this one actually, right? So means x naught is 0, y naught is 0, z naught is 0. So x minus x naught is x itself only. So that's what is giving us the first term. Similarly, if I take the derivative, partial derivative of this with respect to y, then we can find out del u over del y. That term is actually related to y into epsilon yx. Similarly, we can find out a term related to z and so on. So that is how we define these, you can call epsilon xi's or x epsilon 1, 2, you can say. These are related to your strain parameters, UVW, okay? So, well, these are further relations which defines. So, I mean, instead of working in terms of deformation, so in terms of working in deformation, we work in terms of strain components. There is no big difference between deformation and strain components. If we divide with the length, I mean, that is like, okay, deformation per unit length is nothing but strain. So this is what are called these EXX, EYY. So these are EXX is equal to, now X has been removed. This is nothing but per unit X, I mean divided by X. So this is nothing but del U over del X. Similarly, so you can notice here. So this part is nothing but strain part multiplied by X is giving you total change in length. That's the only thing. I mean, there is no much difference as such between them. So this is related to the strain. So we can define, I mean, EXX, small EXX, small EYY, small EZZ, the way they have been defined. So that, and also we can find out what will be EXY. Suppose you want to know what will be EXY or other strain components. I mean, three straightforward strain components we can call longitudinal strain components. So EXX, EYY, and EZZ are longitudinal strain components. Similarly, what are other shear strain components? So EXY, how we can obtain EXY? We can take dot product of X dash with Y dash. I hope you remember that expression for X dash and Y dash. If not, okay, let me take you to the previous slide to quickly have a look at that. So this is your X dash, this is your Y dash. So if you take dot product of X dash with Y dash, what you will find out, this will give you EYX plus EXX into EYX, right? And then EXY into EYY plus EXY plus EXZ into EYZ, okay? And then what we are doing is we are ignoring higher order terms. What we are doing is we are ignoring higher order terms. I mean, the terms which are containing, just a moment, the terms which are containing EXX into EYY, that we are ignoring. Okay, let us do it on notebook. I mean, I haven't done it in the slide, so I request you to take your notebook and take the product. Let me also do on a paper, then we will match our results. So let us take X dash dot Y dash. I hope you are following me. What is this equal to? So you note this. So this will be EYX into 1 plus EXX plus EXY, 1 plus EYY plus EXZ, EYZ, because it's a dot product, right? So X dot X is 1, Y dot Y is 1, and Z dot Z is 1, whereas X dot Y, Y dot X, or X dot Z all are 0. Well, so this gives us what? We have to find out, okay, are we getting this thing? So what we will be having here, first term will be EYX, yes, plus EYX into EXX, plus second will be EXY plus EXY into EYY plus EXZ into EYZ. Now what we are saying is, okay, let us ignore those terms which are containing the product of deformation with deformation itself. So because deformation itself is very small, so that is why we are ignoring higher order terms, higher order products, and we are retaining only first order terms. That is why this sign of approximation. Fine. So that is why we are left with only two terms, EYX plus EXY. Okay. So strain EXY can be followed from this, which is equal to nothing but del U over del Y plus del V over del X, because EYX. So actually, to find out the relation between EYX and this U and V, you have to write down that full Taylor series. I don't know if I should have done it for you, but I assumed that you have done it in your lower classes in detail. So I didn't incorporate the Taylor series as such. So you have to write down full Taylor series. Actually, this is nothing very complex. You have to write down full Taylor series. Okay, let me write this on my paper right now. You follow my wording. So R, capital R, bracket small r, is nothing but equal to, who is trying to join? Vivek Sharma, so late. Okay, so what will that be? R around origin, say R0 plus x into del u over del x, right? Plus y into del u over del y plus z into del u over del z plus x into del v over del x plus y into del v over del y plus z into del v over del z. So one set of components along x cap, other set of components along y cap, plus similarly x into del w over del x plus y into del w over del y plus z into del w over del z. I'm sure it's like, okay, watching a movie without video, but I'm sure you are not getting bored and you are following the audio and trying to write it down what I am trying to do for you. I mean, we are just writing this Taylor series expansion of this around a point r is small r is equal to 0, z cap. Now we on my paper I have all these terms, and if I compare these one by one, then I can straightforward see that, well, this x into del u over del x is nothing but x into exx. Then I have y into eyx is nothing but y into del u over del y, and then z into ezx, I have nothing but z into del u over del z, and so on. So actually that's what was your homework. I don't know, I mean, you didn't do, then you deserve a movie without video, right? But I tried to convey even then the message to you. So that is how you can find out all these values. I mean, strain EXY, EYZ, EZX, and so on. Now, you may ask, okay, what if we have got these? What other useful things we can obtain from them? So, main message of the story is that we can measure these UVW from some experiments. Suppose you have grown a crystal in which we observed that we have some strain has been developed. Then in X-ray, you can find out those UVW parameters. And from those UVW parameters, you can find out further these, what you can call the different strain values, right? And once you know these different strain values, we can find out the vectors back, or once we have the data, I mean, we can do reverse calculations to get these x dash, y dash, z dash. And once we have them, we can find out what will be the change in volume. So then we can define physically measurable quantities. So from simple X-ray diffraction based characterization, we can not only, I mean, it's not only the structure, but there are further many other things which we can calculate from X-ray diffraction data. So one thing is, say, dilation, if you want to find out. So you can find out V dash, and then V dash follows from this. I mean, scalar triple product. I'm sure you all know this. So change in volume, this is what we want to find out. So what will be the new volume when we apply strain on that body or on those reference axes? So this is the new volume. And if we solve this, we will find out this plus some higher order terms, but we have approximated them. We have neglected all terms which are containing higher order products of strain with itself. Now, what will be dilation? Change in volume per unit volume. So V dash minus V, right? What is this? 1, factor of 1 is nothing but v. Why v? Because in our reference system, all the x's, that is x cap, y cap, z cap, had unit length. So what will be the volume? 1 unit, correct? So that is why this 1 is representing the reference volume. So what will be delta? This will be v dash minus v. What will be v dash minus v then? This will be this 1 taken to the left hand side. So v dash minus v is equal to this thing. Now divided by reference volume, which is again 1. So this is nothing but dilation. So we can find out what is the dilation produced in the crystal or in substance because of the strain or stress. Well, then let's come back to those stress components and try to understand them further. So force acting, I mean, this is kind of a similar analysis which we did in the previous lecture on some slides. So force acting on a unit area of a solid is defined as stress, that we have already done. So there are altogether 9 stress components, which I already we have discussed in previous lecture as well, but we will be discussing them now in some specific context. So there is some repetition here, but okay, I mean, there we were calling them, okay, let me go back, what we were calling those, stress and strain. So here we were calling these are like the, say, stress versus strain, or strain versus stress, you can relate it. I mean, if it is force and per unit area, then this will be deformation. And then that is how we can relate the stress versus strain. So these are the 9 components we are talking now, but here the notation is changed a bit. Why we need to redo this? Because we will be discussing some more things from Kittle's book, and that is where this was required. And I kept the notation of the new book. I mean, I prefer to change the notation rather than writing everything again in my own notation. I mean, as per the old notation. So these are those 9 components. What is, okay, then you may ask, what is this XX? So this is like sigma 1, like this is sigma 1, and this is sigma 1, 1, capital X means say 1, small x means second index. Okay, so there were 2 indices, right? 1, 1, 1, 2, 1, 3 there. So the same thing here. So okay, let's try to understand the physical meaning of these first. So now this is suppose the reference volume of our crystal or our material in general. So what is XX representing? XX is representing force acting along X direction on a face perpendicular to X-axis. So this is your XX. What is XY? Force acting along Y direction. Sorry, force acting along X direction on a face. Now this is not perpendicular, right? But on a face perpendicular to Y-axis. So this subscript is representing the surface on which force is acting. But Y means a surface perpendicular to Y-axis. So small x here means surface perpendicular to X-axis. So what will be XZ? Face perpendicular to Z-axis. So how will XZ look like? So this is your Z-axis. So the force acting on this face. It's not shown here, but I hope you can see the cursor. So force acting on this face will be XZ. Well, so this is the physical significance of these X, 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 Y, X, Z. Now we will be talking of something important that, okay, out of those 1, 2, 3, 4, 5, 6, 7, 8, 9 stress component, we are actually left with only 6 stress component. Why so? Now, this is where our that last class's question comes into picture. We had said that, okay, I mean, we are ignoring the translational or rotational motion of the body. What is the meaning of this? Now, let us follow this particular plane. Let us try to look at XY. What is XY? This is your XY plane. So what is XY representing? Force acting on a face perpendicular to Y-axis and acting along the direction of X-axis, XY. So this is what we are saying, XY. This is the face which we are representing. This is xy. Now let us try to look at yx. What will be yx? Force acting along y direction on a face perpendicular to x axis. So this is the face perpendicular to x axis, and this is the force acting on this face and directed along y direction. Are you able to follow me on the PowerPoint presentation, and are you able to see the things in the figure? If everything is fine there.
Yes, sir.
Okay, anyone having any question or any confusion, please feel free to ask. Well, no, then let's proceed further. So now, okay, now this is the force acting this way. This is the force, means xy is the force acting on this face this way. Yx is the force acting on other face this way. Correct? Now, in case these two forces are unequal, let us focus on these two forces first. And there are two components of xy. I mean, okay, this is xy acting on upper face. This is xy acting on lower face. This is yx acting on the opposite face to this one. Now, if this force and this force, suppose they don't balance each other. So what will happen? There will be a net torque or rotational effect because of that. And same is the case here. So in case we want the total torque to vanish, then what should happen? Yz should be equal to zy, zx should be equal to xz, xy should be equal to yx. That's what we are saying here. Now you will ask me why we need to make sure that torque do vanish, isn't it? So this is because if we even take these components not to be equal to each other, that is perfectly fine. But what kind of resultant or what kind of result that will yield? That will yield into this body rotating as a whole, which is sort of a simple classical motion, which can be solved with simple Newtonian equations of motion, right? So, I mean, then we need to consider some center of mass, then rotational effect and moment of inertia and so on. We don't need to go to study of these, what you can call the strain components or stress components, and go to this complex formalism to discuss even simple rotational motion of a bulk body, rigid body, something like this, right? So therefore, to keep our life simple, we say, okay, let us get rid of those translational or rotational motions of the body as a whole, and only restrict ourselves to discuss the effect of strain as such. Strain means you have a body, and on this you are trying to change its length, volume, or orientation, angle, etc. So that's what is the meaning of strain. So that is why we get rid of this, and then we make sure that, okay, xy is same as yx, xz is same as zx, yz is same as zy, and so on. Is this logic clear, or any query on this? Any doubt or question on this? Well, so that's why, okay, again, we are coming to that Hooke's law, and now we are trying to define what are elastic compliance constants and stiffness constants. So now, okay, now let us try to write down the Hooke's law in terms of, now the components has been reduced to 6. So from 9 to 6. Why 6? Because we are getting rid of rotational motion of the body as a whole. Well, so if we are relating strain, so small exx, small eyy, ezz, on left hand side we have strain. We already defined it. On right hand side we have stresses. So capital X, small x is representing stress because of some force acting along x direction on a face perpendicular to x direction, and so on. So these strain components can be related to stress components with the help of this matrix. This matrix is similar to the one which we had discussed in the beginning of this unit. So this is the general Hooke's law for a three-dimensional body, where these here these indices, I mean, one represents xx. We can say, okay, 1 is xx, 2 is yy, 3 is zz, 4 is yz, 5 is zx, and 6 is xy. Why so? I mean, because we want to write them as a tensors. So there we try to write down, I mean, these like, okay, components. So 1, 2, 3, 4, 5, 6. So that's how we are keeping these notifications simple. So similarly, if somebody is writing 1, 1, S11 means it is relating XX strain with XX stress. Similarly, if somebody is saying 1, 2, means it is relating 1, 1 strain with 1, 2 stress. I hope you are, sorry. I mean, if I'm saying S12, this means it is relating XX strain, 1 means XX, with 2 means, what is 2? YY. So it is relating XX strain with YY stress. So 1, 3 means XX strain being related with ZZ stress. 1, 4 means XX strain related with 4 means YZ stress. So that's how we can understand these various components. So these S11, S12, and so on, these are called elastic compliance constants. These are like, I hope now you are able to recall that simple one-dimensional Hooke's law. F is equal to minus kx, correct? So here, what is k? Can we call k as elastic compliance constant for 1D case, or no? No, because in Hooke's law, on left-hand side, what we have is force. So if you divide both sides with the area, then left-hand side will be stress. Right-hand side will be strain somehow. I mean, you can get strain. So therefore, but here on left-hand side, you have strain. Right-hand side, you have stress. So if on left-hand side is strain, right-hand side is stress, then the corresponding constants are called elastic compliance constants. If you do it reverse way, means you are writing stress in terms of strain, because both are related. I mean, if there is a stress, there is going to be a strain, or if there is a strain, there is going to be a stress, correct? So if you are relating stresses with strains, then these constants C11, C12. So I mean, this is just a simple matrix algebra. You can find out Ci's from Si's by taking inverse of a matrix, isn't it? So these constants are called elastic stiffness constants, CII or C11, C12, and so on. So the spring constant K, which we call in Hooke's law one-dimensional, these are like elastic stiffness constants. Spring constant can be termed as elastic stiffness constant. For 1D case, this will be like only this part of the whole matrix will be surviving. Means XX is equal to C11 into EXX. Because there is no Y strain, there is no Z strain, there is no Y stress, Z stress. So for a simple one-dimensional spring, only C11 is non-zero, all others are going to be zero. That's a simple way of looking at it. But in general, for any general three-dimensional object, you may have all of them to be non-zero to a certain extent. They may be small, but non-zero practically. Is this clear, or any question on this? Okay, so meanwhile, you also all sign your attendance in the chat box so that it is recorded. Now, once we have been given these strain components, say all these strain components, we can find out elastic energy density. Just like in case of a spring, one-dimensional spring, What is the potential energy change or potential energy stored in the spring? This comes out to be equal to half kx square, correct? But that is the simplest one-dimensional case, another very trivial one. In general situation, if you have a body which is compressed or which is actually in which we develop some complex strain of any kind, then in general that change in energy or the additional potential energy stored in that body is actually given by this elastic energy density, and this is equal to, the form looks the same, half kx square type, right? This is one strain, this is second strain. So x actually in case of spring is x minus x naught in such. As such it is in case of one dimensional case. I hope you remember that what is the actual strain is half k into x minus x naught square, where x naught is the reference direction. If x naught is 0, we simply call it half kx square. The same thing here. Now here energy is not necessarily stored because of stress applied along x direction and strain produced along the same direction. It may happen that stress has been applied along x direction and strain, some of the strain is also produced along y direction, exy, isn't it? So that is how we actually have to write down the total elastic energy density for any three-dimensional object like this in terms of these strain components. And these are, we can either, yeah, elastic stiffness constants. Now I hope you could relate that half kx square with c. So in this energy expression what will appear, not sijs but cijs, because this is force, I mean stress multiplied by area will be nothing but force is equal to change in dimension. So this, so these are related to k, the spring constant. That's another way of looking at it. Well, once this is done, elastic compliance and stiffness constants defined, energy density defined, then the stress components, we can find them out by taking derivative of energy density with respect to corresponding strain component. I mean, suppose somebody has given you the energy, this U, then from that we can find out corresponding stress component. We just take the derivative of potential energy with respect to respective strain, and that will give us the corresponding stress component. So you can find out the expression for these stress components even if you have been given the energy. So this further simplified, and we can write down this to be equal to this one. I hope you can obtain this expression. Okay, let me give it as a homework to you now. Let me not do it for you. Indeed, I have not done it here in the presentation. Again, today I am giving you a homework, and I'm sure you have a nice weekend coming up. So you will be doing this homework yourself. So you have to obtain that xx indeed is equal to this thing. You try it from this this expression, this full matrix. You try to get that. You have to apply your mind now how it comes. Then this kind of relations we can obtain. Now here, I mean, note that only in this combination, this combination which is appearing in the brackets, there is a factor of half. Why it is coming there? You should try to note yourself why this is coming. There is some double counting happening probably, that's why we are getting this. And there is one more thing which you should notice, that the only I mean combination of, say, if you are getting C alpha beta, then second component appearing in the sum is C beta alpha. I mean here one is C1 beta, then C beta 1. In general, I mean 1 why 1, because we are dealing with XX here. So on right hand side we have 1 here. When we will be doing YY, then here will be 2. When we will be doing ZZ, here will be 3. When we will be dealing with the say ZX or XZ, accordingly you will find different number. So That is why these notations are very important. This one, which I discussed just now. I'm sure you will be in a position to get it done. Now, therefore, what we have is 36 elastic stiffness constants as such. In actual, how many elastic stiffness constants or elastic compliance constants? There are total now 36, right? 6 into 6. This is a 6 cross 6 matrix of Cijs. So there are total 36 elastic stiffness constants. But these, then if you apply this constraint comes because of that that matrix actually itself, that you will be in a position to find out that C alpha beta is actually equal to C beta alpha. So okay, I'm leaving it as a homework to you. This is not something so simple and straightforward. You have to do it as a homework, and then maybe I will ask you to present or whatever. That we will decide later on. So you have to prove that C alpha beta is equal to C beta alpha. This comes out to be so. If so, then what we will be left with? We shall be left with only 21 elastic stiffness constants. Now the numbers are really interesting. Why 21? Why we went from 36 to 21? Yes, can anyone think over this? Why we are getting 21? By simply putting a constraint, C alpha beta is equal to C beta alpha. Yes? Any guess? Rahul and Sandeep. Are you present today? Sandeep and Rahul, are you there? No, Sandeep and Rahul are not present. Okay. So why is the number of element going to 21? Now you try to imagine a symmetric matrix. I hope you have studied symmetric matrices. What is symmetric matrix? For which ijth element is equal to jith element, isn't it? So there are total 36 elements as such, but when you impose the restriction, you take a number of independent elements for a 6 cross 6 symmetric matrix. Then number of independent elements should turn out to be equal to 21. I am sure you will be able to do this. Okay. Again, I'm leaving this as a small thought experiment to you. You try it yourself. Well, then for a cubic crystal, now that is in general, we have any crystal of any kind. But if we have a cubic crystal, means you have some internal symmetry as well in the unit cell. Then in that case, those 21 elastic stiffness constants further reduces to how much? You can count. This is same. I mean, all these C11, C1, C11, C22, C33 will be equal. Why so? Because of cubic symmetry. I mean, whether for a cube you look along X direction or Y direction or Z direction, all will be same, right? So on a simple cubic crystal, whether you apply force along X direction or along Y direction or Z direction, the things are going to look exactly same. That's another way of looking at it. Similarly, C12 and C21 will be same. That is already there because of this. And then all these YZ, ZX and XY, all are also same. And all others are 0 for simple cubic crystals. So this you can prove. I mean, the reason behind this is the symmetry of the crystal. So actually it depends upon what crystal is our material made up of, or what is the internal structure of our material. Then accordingly, how many compliance or stiffness constants are there, that is decided. So for simple cubic crystal, the life is simple. You have fewer elements, and if you start breaking symmetry, then you start getting different number of elements. We are using it as such now. We are using this set of elastic stiffness constants for a cubic crystal, and then further we'll be discussing application of these to derive some properties of simple cubic crystals. I mean, by now you maybe you may have got confused that okay, what is the use of doing this, why we are doing this, right? So once we have these, I mean, suppose you did X-ray diffraction. From that, you found UVW. From UVW, you got back your strains. Then from strains, you could obtain the these stiffness constants. Once you have these stiffness constants in your hand, then what other predictions you can make for your crystal? That's the interesting part of it. So, I mean, before we move to that, these are other properties which we can talk. If for a cubic crystal, we write down the bulk modulus and compressibility. So in cubic crystal, the dilation will be uniform, suppose, from all the directions. Then Exx, Eyy, Ezz is equal to same. Suppose this is 1/3 times the delta, change in volume. Suppose we uniformly compressed our crystal from all the directions. We apply a uniform pressure. Then how we can write down the expression for dilation? Dilation will be 1/3 times delta. And what will be the energy density for case of cubic crystal? This comes out to be equal to this one. Again, we have to generalize that previous expression and put the values of elastic stiffness constants, and that's it. If you write down the bulk modulus, I mean, now this is how we can find out the properties of the crystal. So you have to find out the strains. Then what will be, if you know theseCijs, then you can find out the energy. Then fromCijs you found the energy. What will be the bulk modulus? So this part, I mean, 1/2 into 2/6 it will become, right? Multiply both sides of, multiply numerator and denominator of this equation with half. So what will this be? This is 1/6. So this will be 2/6, 1/3. So basically bulk modulus will come out to be equal to 1/3 times C11 plus 2 C12. So for a cubic crystal, if you knowCijs, you can tell what will be its bulk modulus. Another property we can calculate or predict. Compressibility, this is nothing but reciprocal of a bulk modulus that we can calculate. So this way we can find out various properties from these elastic constants. Now in next class we will be talking about wave propagations in cubic crystals and how these stiffness constants are helpful in understanding propagation of waves in the cubic crystals. So with this, that's all for today. I would be happy if you share your doubts or questions with me so that I can help you. Yes, please. Any questions? Any questions? Am I audible? Are you present there, or you are not sleeping? At least some response should come. Come on. I mean, such kind of dull response is very bad. I sometimes feel I'm talking to myself. So if I'm asking something, so you should quickly say, okay, if you have a question, you simply type a question, or you unmute and ask question. Or if I'm saying a question, you don't have any question, then you say no. Okay, Harish is asking a question. You did this for cubic crystals. What are the difficulties which we will face when we will choose other crystals? There will be no difficulties as such. Only the thing is that we will be finding other components as well. I mean, the elastic stiffness constants will be many in number. So in case of cubic crystal, you have all these CIIs equal. So these will be different. I mean, C11 may be different than C22, than C33. If you have, suppose, a tetragonal crystal, tetragonal A equals B, not equal to C. In that case, we can say C11 and C22 will be same, but C33 will be different, right? So that's how the different numbers will be there. The otherwise analysis will be same. It will follow. I mean, this whole thing will follow as such. And once you know energy, for non-cubic case, you can write down the expressions for, say, for example, bulk modulus. The expression for this energy is going to be
एस्ट्रोलॉजी की क्लास है क्या? इसके बाद अदिति मैम 3 बजे के लिए क्लास के लिए बोल रही थी। हेलो, आवाज आ रही है मेरी?
हाँ आ रही है।
अदिति मैम का फोन भी आया था यार, वो भी बोल रहे थे क्लास के लिए कि 3 बजे लेनी है कि नहीं लेनी है।
4 बजे है हरीश।
एस्ट्रो क्लास 4 बजे?
हाँ 4 बजे है।
तो मैम फिर बोल रहा था उन्होंने कि यदि मतलब तुम्हारे पे कुछ बर्डन है या स्ट्रेस है, अभी ज़्यादा क्लासेस होगी तो वो उसको शिफ्ट कर सकती है मॉर्निंग के लिए कल। तो मेरे हिसाब से कल वाला ठीक है यार, हमने भी चौहान सर की 2 घंटे की क्लास लगाई है, तो ऐसे ही है आज का दिन।
हाँ लगातार है।
हाँ ठीक है, कल
है ना, मॉर्निंग में कल ऐसे भी और क्लासेस नहीं है तो मॉर्निंग में कर देते मैम की क्लास कल।
हाँ कल ठीक है।
हाँ बट मैम करवाएंगे क्या एडिट मेथड?
अबे नहीं यार, कुछ और करवा रही है, बोल रही कि थियोरेटिकल ये सब कुछ। मेरे को लग रहा है जो एनयू मेथड ना वो अलग है शायद, तो पता नहीं कुछ बोल रही थी, लगना पता भी। हो गया सर, आएंगे ना कि नहीं आएंगे?
पता नहीं, रिकॉर्डिंग चालू है अभी तक।
हो गई हो क्लास?
टाइम भी हो गया यार, 18 बंदे यहाँ पे।
सर ने लेफ्ट तो कर दी मीटिंग।
सर ने नहीं लेफ्ट करी होगी, सर खुद ही वहाँ पे सिग्नल नहीं होना था ना, तो निकल गया होने खुद ही। चलो हो गया फिर क्लास लीव।
रिकॉर्डिंग
ये सर को कॉल ही करे, मेरे पास नंबर भी नहीं है, ग्रुप में था पड़ा।
टाइम तो हो गया, सर चले गए होंगे।
मेरा आदित्य मैम का कॉल भी आ गया, चलो मैं बात कर लेता हूँ मैम से, नहीं तो वेट करते।
कल सुबह ही बोला।
अभी इधर को कॉल आया था, अब बोलता है कि जिस नंबर पे आप कॉल कर रहे हो वो अस्थायी रूप से सेवा में नहीं है। चलो लीव कर देते यार, फिर 3-4 तो हो गए।
हाँ
ठीक है।
मैं उम्मीद कर रहा हूँ। ठीक है, हाँ ठीक है हरीश।